Okay, take two. And 15.9, the Jacobian is what we're going to be looking at. And basically, it's about changing variables. And we have already done that a little bit in Calc 1. So we're going to do a little comparison from what we did in Calc 1. And I just want to give you my favorite integral to ask people in Calc 1, which is this one, x sine of x squared. People that have taken me for Calc 1 know that this is my favorite one, from 0 to the square root of pi. And what you're finding is the area trapped under this curve at y equals x sine of x. So I'm going to go to computer screen. I'm going to go to back here to and here I have a graph of it. And so y equals x sine of x squared, from 0 to the square root of pi. And we were finding the area that's trapped under this curve, between this curve and the x-axis. That's what we were finding. And our problem was, so I'm going to go click back to OBS here, click back. Whoops, I went on the wrong spot. Back to paper view. And the problem was, well, we couldn't integrate that to find the area. I mean, we definitely could appreciate that our bounds were going from 0 to the square root of pi, and that was along the x-axis and all of that. But we couldn't integrate that. So what we did was we had this sneaky way of going around that. We said, well, if I let u be x squared, and then du equals 2x dx, and so this made kind of a transformation, and we changed the bounds, and I'll let you change the bounds, but if you do, the low bound becomes u equals 0. If you put in x is 0, you get u is 0. And the up bound becomes u equals, if you put in the square root of pi and you square it, you get pi. And so it goes from 0 to pi. I said I was going to let you do that. I never let you do anything. That's how I am, I know. And but you get half sine of u du. And so I just want to show you this. And so I have to go to not stop recording. I have to go to computer screen. I have to click on here. There is our original. Look at that area under the curve. And here is the area under this curve. And they have the same area. So the area from the curve, the x-axis to the curve, it from 0 to pi, is exactly the same as the area from 0 to the square root of pi under this curve, trapped between this curve and the x-axis. And so that's pretty freaking amazing. Back to OBS, back to paper review. And that was, instead, it was from 0 to pi along the u-axis is what we had. And I want you to pay attention to this half, because I'm going to tell you something about it here in a second. And we also did this with our double integrals, and we also did it with our triple integrals. I just wanted to show you just real quick, not real long. This is where I had to stop the video and start again, because I forgot to show my computer screen, and I talked all about it without showing my computer screen and felt really silly. But this is what, if we wanted to integrate over a circle, this is what you would have on your inner bound of your double integral. Is y equals negative, say, for the circle, square root of 25 minus x squared, and you would be going to positive y equals positive square root of 25 minus x squared. On the other hand, if you change to polar, you're not only changing you're changing from the rectangular coordinate system, but you're also changing to the polar coordinate system. But look at the equation difference. R equals 5 is what it is. That's going to be a heck of a lot easier when you plug it in and have to integrate with it, and also when you plug in with it, and also when you try to take that second integral. It's a heck of a lot easier. But there was some things we had to do to make that transformation, and we were going then from R from 0 to 5 in order to get all of it. Okay, back to not going to that anymore. So OBS and to pay-per-view. And so anyway, so that was kind of the story, that we were making a transformation. And so so for double integrals, So for a double integral substitution, we must also change the region. So we're going to look at this. The region R by a transformation. I hope I can spell transformation. Well, it's kind of late at night to be spelling things like transformation, but I'm not complaining. I'm happy. From XY is an element of R. 2, and then you can call it your substitution whatever you want. So you can do U and V. That's pretty common to use U and V, because this is an ordered pair that we're substituting, which is going to be an element of something new, something different. So here was along the x-axis, then along the u-axis. So from R, and now call it S, whatever you call it, just because that's next in the alphabet. And so the things about this transformation is that you should get this transformation. So just a little filling in here is a 1-to-1 relationship between R and S. So it gives us this relationship between R and S. And I can kind of draw this relationship. You have a point right here, and this is in R, and that point looks like X comma Y. And then what you're doing is you have another universe over here, and it doesn't have to look square. It can look, or circular, it can look square. You have another universe over here, S, and you have a point in here, U and V, an ordered pair. And then you're transforming that point to that point. And you're doing that for every single point in R to a point in S. And so that's kind of the story. And so is a one-to-one relationship between R and S, and defines how X, Y, that ordered pair, and U, V work together. And so that's kind of the story on that. And what we're going to be looking at in this section particularly is, well, what if you were trying to integrate over an ellipse and not a circle? So we had a method of doing if it was a circle. We had a method of doing triple integrals if we were going over things that were spheres or cones and those kind of things, and spherical coordinates as well. So we kind of have 3 ways there. Anyway, long story short, but what if you had an ellipse and you were trying to do over a double integral? Well, we don't have a method right now. And what if instead of we did some that were square, those were the very first ones we did, squares and rectangles, but what if it's a parallelogram instead? Well, then we're going to learn how to make a transformation. Now, when we make this transformation, there's something in there that's a little bit extra. So it's not just the variables, dA, when we change it, and when we change it to some other thing, there's something extra, and that extra thing is called the Jacobian, and its variable is J. And my computer in font, the font that it has to use doesn't make that J happy, and that J does have an absolute value around it, so it's positive. And so I don't like the way it makes the J, so I have to go over it and write the J again. Anyway, so that's kind of the story on that. And that J there, which is an absolute value. So it's not exactly the same, but it's kind of a similar idea to that half right there. It's just a similar idea to that half. So we didn't call that half the Jacobian, but it's a similar idea to, it's something extra that we need. So I have here, what is in the world is J, and I'm fixing my J, of course. And J is the Jacobian, and it's a determinant of a transformation of 2 variables. Given a transformation T that takes us from X equals some ordered pair UV and Y equals H at UV, where G and H have continuous first partial derivatives on the region in the UV plane. The Jacobian determinant, or the Jacobian of T, is, and then this is the Jacobian, and it is a J, is what it is. And I'm sorry, I'm not very good at that. I don't, the font's not good there. And but it is a 2-by-2 determinant where you have the partial derivatives. Again, do you guys know that? Partial of of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. And so first we're going to just practice finding the Jacobian. Then we're going to go and we're going to do the whole thing. And so we're just going to do the part out of context. So let's say that we had some double integral that we were trying to find, and we wanted to make a transformation, and we were going to let x be 2u plus v, and we were going to let y equal u squared minus v. And so what we would want to do then is you need what's called the Jacobian is what you need. And so we're going to find that Jacobian, and so here we go. Here we go. And so it's the partial of x with respect to the partial of u. And so I am trying to make these partials. And I know last night I was so tired that I was pretty crazy on how I made my D's, and I was sorry about it later. So I want to go to x, and I want to take the derivative with respect to u, and v is a constant, so that's just 2. Then I'm going to do the partial of x with respect to v. And I'm going to go here to x, and I'm going to take the derivative with respect to v, where u is a constant. So that is the derivative of a constant is 0. The derivative of v is 1. So this is equal to 1. And then I want to go and I want to take the derivative, go to y, and take the partial derivative with respect to u. And so I'm going to treat v as a constant. So do you guys agree I get 2u? And I want to do the same for v, and I get -1. Then how you find the Jacobian, it is a matrix, and here's my matrix right here. And so, and I put them purposely in this square when I found them, so that I can just fit them right in here, right? So this is 2, this is 1, this is 2u, this is -1. And then you just do the determinant. So when you do the determinant, you multiply these together and you get -2. And then remember, you subtract, right? And then you multiply these together and you get 2u. And that's the Jacobian. So that's how you find it. And so, and we're going to practice it on one more thing, and then we're going to learn how to use it. I was so cold that I got my heating blanket off my bed and put it on myself. And now I'm feeling like, oh my gosh, I've set myself on fire is what I have done. And so I might even have to take off my sweatshirt. And I had my hood up too. And I mean, it's crazy around here. Okay, now I want you to find the Jacobian for this transformation. And we've already done this transformation. X equals r cosine theta, and y equals r sine theta. And I hope that you're remembering that when you did the integral, when we did the integral and we had made this transformation, when we had gone to polar, there was something extra in there. Do you guys remember what it is? So I'm going to not tell you. I'm going to let you guess. And so anyway, so let's see if we can find it. So we need the partial of x with respect to, in this case, we have r and theta. So we're not going to do u and v. So with respect to r, and that is equal to, so I'm going to keep, r is our variable and theta is a constant. So the derivative of r is 1 and the constant just holds still. So this is equal to cosine of theta, and then dx d theta here. And so I'm taking the partial there. And when I do that, the r holds still, and the derivative of cosine is negative sine. So this is negative r sine of theta. It's not just my pet peeve when people write it like this. It's wrong. And even if you put the time sign in here, friends, it's not right. And so it's confusing. it looks like subtraction and like there's a fleck of eraser dust on your paper there as your little time sign. So if you insist on writing that way, you can, but what you have to do is you have to put in parentheses. And so um, in order to be correct, and so I want to erase all this because I don't really want it, but I did want to take the opportunity to tell you that it's not just me. You're going to find that everywhere you go, and 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 so and I hope that you have to do math for a living. I hope you do, because people who have to do a little bit of math on their job for a living make more money. And so I hope that you do so much math on your little job that when you get out there. Okay, I got to take the I gotta concentrate. I gotta concentrate. So go to y with respect to r, so that's sine of theta. And then right here, with respect to theta. And so now r is a constant and the derivative of sine is cosine. So r cosine theta. And then I want to find the Jacobian. And so we got here cosine theta minus r sine theta. There's the eraser dust that I was talking about. And here and here. So when I do my Jacobian, I'm going to write it underneath so that I don't get on that line. I hate that when I do that. And so here I'm going to get r cosine squared theta when I multiply these together. And then remember that you subtract, and then I'm going to subtract this. But when I multiply those together, they're a negative. So I'll put a parenthesis, negative r sine of squared theta. So when I double subtract there, right? Subtract of a negative, that's an add, of course. And I can factor out the r at the same time. Is that okay? 2 steps because you're in Calc 3. And I'm about to make a third step right here on you that I bet you already are seeing, and you're like, oh my gosh, I can't believe it. That's 1, right? That's a Pythagorean identity. So this is r. And so I hope that you were shouting that at the screen, because r d theta, right? R was the extra little piece. And when we went in there and we just proved what it is, and it has a name, that little extra piece, and that little name is the Jacobian. So I can't help myself, r d theta, right? And so you already knew that. And so on we go. Hot diggity dog. You're like, oh my gosh, this is so fun. I love this so much. Okay, so what we're gonna do, oh, and I forgot that I wanted to, oh, this is just finding the Jacobian. There was the one, and I wanted to put it on Desmos, and I forgot. That's how I am. Okay, so find the Jacobian for the transformation, and we have here x equals 2u. Can you see that? 2u plus w, y equals u squared plus minus v squared, and z equals u plus v squared minus 2w squared. So this is extending it to 3 variables. And so what the Jacobian would be if you extended it to 3 variables, then I'm going to write it right here. Then my Jacobian, there's my J for my Jacobian. It would be a determinant that is 3 by 3, and it would be dx, the partial with respect to u, and then with respect to v, and I have w then, and with respect to w, and then the same thing, a row of these with y with respect to u, and y with respect to v, y with respect, right, partial of y with respect to w. So I'm gonna quickly write those in here and try not to have any typos or leaving anything out. I know I sometimes leave something out when you guys are yelling at your screen. Put that in there. And I need one of you to come over to my house and tell me what I am messing up on. Everybody is not volunteering now, right? Okay, so we're going to find these pieces and then we're going to do the determinant of it. That would be the idea. So so I'm going to take the partial with respect to u. Here I get 2. With respect to v, well, there's no v's there, so I get 0. And with respect to w, so w is the variable and everything else is a constant, so I get 1. And then I'm going to move on to y with respect to u, so that's 2u, and then minus 2v, and then there's no w, so that's 0. And then here on the z's, u with respect to u, 1, and I thought that had a u in it, but it doesn't. Okay, and then here 2v and minus 4w. And then I just have to do the determinant there, right? So my j, my Jacobian, would equal, and then I don't know if you remember, but you go 2 times, and then you put your finger over the column that had 2 in it, and then you do your you do your 2 by 2 here. So when I multiply these together, I get negative. I better have this be a little bit bigger. A negative times a negative is a positive, so that's 8 VW. And then you're going to subtract going back this way, right? Subtract going back this way, so minus and then 0. And then I don't know if you guys remember, but then in order to do the 0 here, it would be minus and then 0 times whatever you got. And I'm just going to allow myself not to have to do that. But of course, because it's 0, you would do those, this 2 by 2, this 2 and those 2, right? Crisscross, applesauce there. And then it would be back to plus. So it does alternate sign, the determinant. And then I get 1, right? So that's I think we called that a pivot point when I was growing up. And so here now I'm going to put my finger over these. And so now I'm using these is what I'm using, right? Because my finger is over those. So I'm getting 2 times 2 is 4 UV. And then you're going to subtract. And then I have a negative when I do that, so it becomes a positive 2v. And then when the dust clears, this is what I'm going to have for my Jacobian. I'm going to have 16 VW. That's gone there, and then plus, and then 4 UV and plus 2V. So that's my Jacobian. So anyway, so we did a lovely job on finding the Jacobian, even on a 3 by 3. And so anyway, okay. So we're going to try to evaluate this region. And I just wanted to just quickly, and I wish I would have already had it set up, but I didn't do that. And so, but I do want to show you, I can't help myself. So I want to go to my Desmos, and I'm going to just pick up this one here and delete this out right here, and then just quickly put in. So I have y equals negative, I didn't put equals negative 2x. And then I have y equals, because I want to show you how this is going to help us here. And I'm going to put 0.5 for half x minus 15 over 2. And y equals and minus 2x. Don't worry, I'll get it on the screen. Well, hopefully I'll get it on the screen. Plus 10. And the last one is y equals, this is the region I'm integrating over, 0.5x. And so that region, and I hope that you can see it on the screen that I've made right there. This region right here is it's a rectangle, but you notice it's tilted on its side. And so, so it is a parallelogram, but that's really hard to integrate over, because I don't know if you remember, but what you would have to do is you would have to go from a y value function, so you'd have to find the equation of this line, which you know, to another y value function, and that would be a double integral there, but then this is a different y value to a different y value, so it would be two double integrals is what it would be to solve this is what it would be if we use that. And I'm going to show you that by making this little transformation that we're going to make it a little bit easier than that. So certainly we could solve it that way. I mean, that would be a way of doing it. So what we have been told, though, is to use this transformation. So they've given us a hint here to get us started on how to do it. So how you do it to make, and this is what we're trying to integrate right here, and don't worry, we're going to do the whole thing here. And oh, did I show you oh yeah, I did. I showed you with the Jacobian in there, right? And so, and I'll write that up. And so we're going to go from this integral right here, and we're going to turn instead, we're going to turn our integrand into u's and v's is what we're going to have. And instead of having either dx, dy, we're going to have the Jacobian du, dv, or the Jacobian dv, du, because that's what we're changing into, u's and v's. So that's what's going to happen. So real quickly, equation 1 looked like this: y equals negative 2x. They told us to let u be x be u plus 2v and y be v minus 2u. So where I see y, I'm going to write v minus 2u equals, and then minus, and then x was 2 times u here, u. I can't say that. I'm not going to say it. I'm just going to plug it in. And what I want to do is I want to make that look a little bit nicer. And so when I distribute here, and I hope that you notice that, well, negative 2u on this side and negative 2u on this side. So if I add 2u to both sides, right, add 2u to both sides, and if I also get the v's on one side, because I want to solve for v here to make it look a little bit nicer, so I'm going to add 4v, and I'm going to add 4v. So when the dust clears, all of the u's canceled out, and I get 5v equals 0 on this side, right? Everything's gone. So that means that v equals 0. So instead of this equation, x equals negative 2, x equals negative 2x, what I'm going to have instead is v equals 0. And so that's what I'm going to have. Now, the second equation is y equals 1/2 minus 15 halves. And same thing, we're going to do the same thing. So v minus 2u. So I'm plugging in half. And so here is u plus 2v. And then I'm trusting and making it look nicer. So when I go and try to make it look just a little bit nicer. Now, the first thing is that I have the half in there, and before I even started, you know what I should have done? And I'm gonna back up and I'm gonna do that. And I just forgot to do it because I was tired and I was sleepy and I was hungry. I was none of those things. I was just joking. Is I'm going to multiply by 2 to clear the fractions, just to make it look a little bit nicer. It's the same equation. So 2y equals, and then when you multiply by 2 here, you get x. And when you multiply by 2 here, you get minus 15. So when I plug in here, I'm going to get 2, and then y was v minus 2u equals x, u plus 2v minus 15. So when I make that look a little bit nicer, are you making yours look nicer? I noticed that I got balancing 2v's, negative 2v on both sides. I also want to get the u's on one side, so minusing u to the other side. So when the dust clears, I get negative 5u equals negative 15. And so that means that u equals 3. So these are my new, this is what I'm now integrating over. U is 0 and, excuse me, V is 0 and U is 3 so far. And I've got 4 equations to do, so I'm solving along. And if I have any fractions, I'm going to remember next time to get rid of them first. It makes it easier. Why not? But I don't have fractions here. Why? So I'm going to plug this in right here. Plus 10. I was like, isn't that the same equation I already had? And then my eye was not catching the plus 10. So it can happen. So balancing negative 2u's. So if I add 2u to both sides, the u's totally go away. I want to get the v's on one side. So when I do that, I get 5v equals 10. And when I solve that, I get v equals 2. And so you can see that all of these equations are nicer than the equations that I had. And I'm going to make a sketch of them myself. I won't even go to Desmos. And I have one more to do. And I'm going to put it right here. And so I'm kind of boxy person, you know how I am. And so y equals 1/2 x. I'm going to multiply and have that 2v equals x. That's just easier to deal with, multiplying by 2. And then I'm plugging in y, what y was under our transformation. So this is our transformation equals, and what x is under our transformation. And then I'm solving it to make it look a little bit nicer. And I notice on this one, as I'm looking at it, that the two v's are balancing. So they're going to drop out. So minus 2v. And I want to get all the u's on one side. So you could add 4u or you could take away u. I think I'll take away u so that just because it makes me happy to have my stuff on the left over there and divide by -5, but I get u as 0. And so that's the hot diggity dog part. Okay. So I can make a drawing of the new. So remember, it was a crazy rectangle that was on its side, and we would have had to do 2 double integrals in order to find, this is the height, right? And so we're finding the volume is what we're finding over that rectangle, and this is representing that height. And we would have had to do 2 double integrals to do that, which is a lot of work. And so what was I going to say? I had something to say here, and I was going to write it right up there, but now I don't remember what it was. Oh my, worried about myself here. And so the other thing that we need, I was going to draw this. Okay. So here our new thing, right? And in fact, I'll draw it right here. So here's our new thing. It has a V axis and it has a U axis, and U equals 0. So U equals 0 is right here. And V equals 0 is right here. And I don't know why I didn't draw that straight. U equals 3 is right here at 3. And V equals 2 is right here. So we're going to be integrating over this. And that's the very first thing that we started integrating over, is things that were rectangles. Okay, but we need one more thing that we haven't got, and then we'll be ready to make the switch, the transformation. What are we missing? We're missing the 1/2, right? Okay, it's not 1/2, but whatever it is, it's over here. It's that same idea as when we did this. We got this something extra. And what did that something extra called when you have triple integrals and double integrals? It's called the Jacobian. And that's what we're missing. So we have to now find the Jacobian. Now, there's some other notation that I want to show you that you can use as well. for the Jacobian right here. And you can use this notation that I don't know if where I got this notation. I made it myself. I hope I didn't. Gosh darn it. You're not supposed to go around making up your own notation. But this is the partial of x with respect to u, the partial of x with respect to v. You have to admit that that's a lot easier to write. And I tell people that you should write out something to let me know what you're finding, because you just start putting numbers in a matrix or variables in a matrix and you don't have them right. And then I'm like, I have no idea what you're trying to even do. Do you even know that it's supposed to be the partial derivatives? And so you do want to take the time to write that out, because it is easy to make a mistake when you do so many of them, quickly on a test and you're nervous. So with respect to u, that's 1. And with respect to v, that's 2. With respect to u, that's -2. With respect to v, you should go in alphabetical order, that's 1. So the Jacobian is 1, and then minus, and then -4, which is equal to 5. Okay. So very good. We did a lovely job on that. So we need the Jacobian. Now the other thing that we need, so now we're going to start on here, just kind of, I don't know why I made a line right through that, gosh darn it, you ever wonder about yourself, I'm not crossing that out, just making a line. So we have this region right here, and we had x plus y dA. And what our plan is instead of integrating this over dx dy, our plan is to change this into u's and v's. Now we know what x is. X was u plus v. So this is going to be the double integral. And then instead of x, I'm going to have u plus 2v, because that's what x is. And then I'm going to have plus, and then y, right? I hope you can see that. And then y equals v minus 2u. And then, so this is going to be my new integrand. This is x, right? This is y, and it was x plus y. Now the part I'm forgetting is times the absolute value of the Jacobian, and the Jacobian here was 5, but I am putting the absolute value around it because it is the absolute value of it, and I don't want us to forget that. And then I get to choose if I'm going to go du first or dv first. And so that's absolutely 100% my choice. On this particular problem, it does not matter at all which one that you do. Do you guys agree? Half dozen each to the other. We're going to have numbers on both bounds. See how u is from 0 to 3 and v is from 0 to 2. So I'll just do an alphabetical order. And so I'm going to go ahead and put right here du dv. And so then my bounds will be for u from 0 to 3 and from 0 to 2. So that when I work this, u minus 2u is -u, and then plus 3v. And the 5 can go, the absolute value of 5, that doesn't have any variables in it. It possibly could have variables in it. On this particular example, it doesn't. And so I'm going to put that in the front, the 5. And the absolute value of 5 is 5. And then du dv. I don't often put constants out in the front. And the reason that I don't is because I get questions like this. Would it be okay for me, if I was integrating this, to put the 1 out in front? And the answer is, or change it into a 2 if you want. Can I put the 2 out in front? And just because 1 was a common factor, so I was being careful about that. And the answer is no, you can't. Only if it's a product can you put it out in front. And the Jacobian was a product. So you could put it out in front. Anyway, just like the half when we were doing the sign one that we had over there. Okay, so I'm going to integrate this with respect to u first. And so as I do that, I like to put a box around it because I'm kind of a boxy kind of person. And no, I cannot put the 3V out in front. When I integrate that, 3V is a constant, and I'm taking the integral with respect to u. I have to really tell myself that. So this is going to be negative u squared over 2 plus 3uv, and u's go from 0 to 3. So when I put in here 3, I'm going to get negative 9 over 2 plus 3 times 3 is 9v minus, and then putting in 0 for u, I'm going to get 0, I'm going to get 0, so minus 0. So it's just negative 9 halves plus 9v is what's going to go in that box, right? And so I like to do that box, and then I like to go like an arrow over and put all the stuff so I don't forget it, like the 5. And from 0 to 2, I might even remind myself that those are bounds for v. And I'm going to have the negative 9 over 2 plus 9v dv. And no, it's not okay to move the negative 9 over 2 out, and I wouldn't move anything out. Now, some people might tell you that, hey, you have a 9 in common, and so you could pull out a 9 from both of them. And certainly, you're right on that. I probably wouldn't. And so, but whatever, I mean, you can do your own algebra. So this is v plus 9v squared over 2 from 0 to 2. And so I haven't forgotten the 5. I'm going to multiply by 5 at the end. So the up bound, so that when I put that in, I'm going to get negative 9. When I put that in here, I'm going to get 4. I'm going to divide it by 2. That's going to give 2. So it's going to be plus 18. And then plus a 0. And so altogether, that gives me 9. But don't forget to times it by the 5, right? We still have the 5 hanging out here. I a lot of times will put it like this because I'm worried I'm going to forget it and carry it around. And so, yeah, 45. Would we have gotten the same answer? Yeah. And this was a lot of work, I have to admit. And so, but it's a way of going. Sometimes it's impossible, and you have to really, you have to redo, is what you have to do. So we did a lovely job on that. It wasn't so bad. It was pretty happy. It was really good. You loved it. Everybody loved it. Your mother loved it. Invite her in and say to your loved ones, look at these cool videos. Like and subscribe is what what you can say. So this is example 5, and I have this, right? And it's in the rectangular coordinate system. And the region R that we're going to be integrating over is do you recognize that? It's not a circle. And so since it's not a circle, what that means is that we can't, since it's not a circle, we can't use polar coordinates. And so that's the problem, because x squared plus y squared equals r squared. But what do you do if they have coefficients of 9 and 4? And that's the problem. Now, what you normally would typically do with an ellipse is you would typically divide by 36 in order to get 1. So this is an ellipse, and you would typically divide by the 36 to get 1 on one side. So when I do that, I'm going to get x squared over 4 plus y squared over 9, like this is the common ellipse, right? Equals 1. And I certainly don't want to solve that for x or y and then try to use that, whatever you solve for on the inner bound, y equals some crazy square root thing that I'm going to plug into this crazy square root thing. That would be, that would be not good at all. And so what I want to do is I want to use a transformation that when you have an ellipse that turns it into a circle, that's what I would what I would like to do. And so that's kind of the idea. And so what you want to do is in order to turn it into a circle, you want to knock out the denominator. And so I'm going to just show you that I want to put something x equals something, and I want to put right here parentheses squared, and I want to put that in here, and I want it to cancel out the denominator of 4. So you already know what you're going to put in here, right? A 2, because 2 squared is 4. Now I'm canceling out the denominator. And what else do I need? Well, I need a variable like you. And so you would be a great variable. So what I'm going to let x be is 2u. And what do you think, friend? Um, what are you going to let y be? I hope you figured it out. 3v? That'd be great. So, so how that changes our little lives is that when you put that little u substitution in here, then what you get instead of this ellipse is you get u squared plus v squared equals 1, which is a circle. And if you're integrating over a circle, well, then you can use polar coordinates, but um, you have to have the Jacobian. And so so that's the next thing that I got to find, right? And so right here, I'm going to find my little Jacobian, and then I'm going to get busy putting all this stuff in and hope that it works out pretty good. And so I'm going to have here x with respect to u, x with respect to v, y with respect to u, y with respect to v, and I'm going to do the determinant of that. So when I do, now this is just 2, and then with respect to v is 0. So it actually is pretty nice as well. And then here is with respect to u is 0, and then this is 3. And then I get, when I multiply them together, I get 6 minus 0, which is 6. So the Jacobian is 6. I'm still going to hang the absolute value around it, because I noticed last semester that all of my little examples had lovely, lovely, lovely positive values for the Jacobian. And the very first example wasn't very too far into it that I did one in the book, and the Jacobian was negative. And I had forgot to put absolute value around it because I had gotten kind of, well, there are Jacobian's positive, but it needs to have absolute value around it. So I'll remind you of that. Okay, so I'm going to take this integral right here. I'm not going to write that integral out just because I'm gonna save a little bit of work room here, but it's a double integral, and right here for x, I'm going to put 2u, and so this is the square root of 1 minus, and then 2u, because you substitute not only squared over 4 minus, and then 3v. So not only did it help us over here on what our bounds were that we're going to have, but it also helped us, this is over 9, on what our integrand was, because this is going to look a lot nicer on this particular integrand as well. You're going to see that it's going to turn out not too bad. Now, the other thing that I don't want to forget is my Jacobian. So the absolute value of 6, I'll put it right there. And I'm going to have whichever one, du dv or dv du, whichever one you think would be best. But I'm going to tell you, friends, that I don't plan on actually using either one of those, because I'm going to do another transformation right here, because what I have, if I wanted to do this with du dv, I'm going to draw this in here. And if I wanted to do that, then I'm going to call this v, and I'm going to call this u. You do them alphabetical order, right? And I got this circle of radius 1. Well, if I wanted to go from here, because remember, you go from function to function on my bounds, then I would be going here and I would need to solve this equation for V. And so I guess I would need to change this to, if I'm going to go this way, to dv, and this would be down here, that function, solve for v would be v equals the square root, and it'd be negative because it's below negative 1 minus u squared. And that's what I would have right here for my lower bound. And so I'm going from here to here. That's what I would have. And my upper bound would be the top half of that circle. Can you imagine? And then I would try to integrate this thing, which I'm not even sure how I'm going to integrate that. I mean, it would be such a mess. And so no, 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 that's not the plan at all, right? That's not what I'm going to do. I'm going to change this from u and v into, because it's a circle, into my friend polar, right? And so what I'm going to do, so I'm not going to do this. What I'm going to say is that I know that u squared plus v squared equals 1. That was a 1. And what did I write? An r. And so that means that r squared, because that's what u plus v squared can equals 1. And that means that r equals 1. And remember, r is positive, right? And so when we go to do this, instead of getting all of the circle in this way, right, and then going back this way, right, instead of doing that, that's not how we're going to do it. How we're going to do it instead is we're going to let our radius go from 0 to 1, right, out to here. And so that's going to be on our inner. So I'm going to go here, and I got to fix up my underneath there too. And I still have my 6, absolute value of 6. And so, and then I'm going to have, because I'm not going to do u, v and u, I'm going to do, I'm going to do r and theta. And I already know what the Jacobian is. It's r d theta. Now, if you're wondering, why don't I have to have absolute value? Why don't I put absolute value right here around the r? So why don't I do that? And I hope that you're yelling at the screen. The reason I don't have to do that, and we never mentioned that or said anything about that before, is because r is a positive value. R goes always is a positive value. It's a length, right? It's a distance from here to here. And so our R value is going to go from 0 to 1. And I want to get all of these all around the whole entire circle. So this is going to go from theta. So this is for R in the inside. For theta is going to go from 0 to 2 pi. And we have r d theta. And then I have some fixing up yet to do. I probably should have fixed that up. Do you guys agree that 2 squared divided by 4, so that's just u squared? So I wish I would have written that out before, because I want to fix that up because I'm going to u here. But underneath the square root, just let me write it up here if you don't mind. Underneath this square root is 1 minus u squared minus v squared. Is that okay? And how I'm going to write this is the square root of 1 minus, and then I'm going to put parentheses u squared plus v squared. And I'm sorry I had to write that up. It's just that I forgot to do it, and so I lost my momentum right there. And I want this all to be r's and thetas, and those are still u's and v's. Do you guys see where I'm going to substitute in and change that into r? That's going to be 1 minus r squared, right? Because u squared plus v squared equals r squared, right? And so that's what we're going to have right there. Probably should have wrote that here. U squared plus v squared equals r squared. And we know that this equals 1, right? And so I don't know. Do I need to write that there? You guys are like, no, you don't have to write that there. This equals 1, and I know that u squared plus v squared equals r squared. So r squared equals 1, and r equals 1. I guess I should have maybe put that. I don't know. No, you're saying no, I don't have to. Okay, thank you. Minus 1 minus r squared. Okay, so I have this now, and I need to find the derivative of it. I can certainly put the 6 out in front. Can you put the r out in front? No, because you're taking the derivative with respect to r. So you can't put the r out in front. And the reason you didn't need absolute value on the r, even though it's the Jacobian, right? And two Jacobians in this problem right here, right? The reason you didn't need is because r is positive. So I didn't need that around. I didn't need absolute value around it. I didn't need absolute value around the 6 either. Why did I put absolute value around the 6? Because I didn't want you to forget that it is absolute value. So if you solve this problem, you can get the 6 out here, and you can go from 0 to 2 pi, 0 to 1 of r square root of 1 minus r squared, uh, dr d theta. And I got the r right here. And what you're going to do to solve this problem, I hope you know that you're going to do, because you're going to do this inner part right here. That's our first step, right? And you're going to do a u substitution to do that, right? That'd be 1 minus r squared, and then du equals da 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 da, right? And then you're on your way. And I told you guys that, hey, you finish it up. And when you finish it up, I think that you're going to get 4 pi is what I think you're going to get. And so anyway, so that's the story on there. And I have confidence in you. Okay. Last problem for us to do, and then I have a problem for you to do on your own, if you like, and if you want, we can look at it in class as well. And so here we are on this problem right here, and so what do you think? So I have xy squared dA, where the region is bound by xy equals 1, xy equals 2, y equals x, and y equals 2x. If I was to draw that, then what you have there, x times y equals 1, is a hyperbola looking thing, is what it is. And xy equals 2 is a hyperbola looking thing. They have curve. I'll just draw one of them. This is the one that equals 1. This is the one that equals 1. You have the two pieces of it. And so then we have one that equals 2. It would be good to do it on Desmos. So we're going to have some curve in here. I'm not even sure which one's in there. And then we have these lines going here. And so we're making some kind of, and it's got these curves is what it's got kind of going on. And this is the line y equals x. I didn't draw them to scale, and y equals 2x is a little bit steeper over there. And so, and in fact, they kind of stem from the same spot. And so I wasn't meaning to be exactly accurate with how I drew it, but something like that is kind of what we have going on. And so that would be really, really hard to integrate over, because then you would be trying to pick a spot and going from here to here. And do I stay on the same curve? And the answer is no, I don't. I would be on a couple different curves. I don't even know, because I haven't drawn it big enough to sketch it out. But right now I'm thinking 3 triple integrals is what it might look like it would be. And so I want to come up with a transformation that would make sense and would work. And so what I got this problem from Professor Leonard, and what I was in the habit of doing is watching some of his lesson and then trying it on my own. And so what I looking at the problem, what I said to myself is, well, what I would let one of my transformations be would be u equals xy. Do you see why that would be kind of nice to let one of my transformations be? So I said I'm going to let u equals xy. And then I was looking at it, and that takes care of these because that becomes u equals 1 and u equals 2. And that's really nice because those are um, horizontal lines. No, vertical lines, right? And so instead of these curvy stuff, you got these vertical lines. So then I was looking at this, and those are lines that are slanted. And again, I don't want that. But I just noticed, and I don't know if you notice, but like if you were to divide by x in these equations, both of them. So if I took and divided this equation by x, this equation would become x over y over x equals 1. And then I'm going to mark it out because I just replaced it with this. And then if I divided this one by x, it would be y over x equals 2. And that's how I found my other transformation. I felt so proud of myself. And so we have this. And then the only way that I'd seen the problems done is so far, and it was by having it solved for x and solving it for v, right? That's how when they gave me the transformations here, x equals blah blah, y equals blah blah, and right here x equals blah blah and y equals blah blah. And so I was like, and I mean, I whipped out a system of equations so that I could solve my very clever things that I thought were very clever for x and for y. And then I told Arnie about that because I said, "Is wouldn't it be nice if there was another way of doing it?" And Arnie said, "Yeah, there is." Now, the only time that I really need to know what x and y are is when I find the Jacobian. So because equation 1, I'm going to label him here, equation 2, equation 1, which was xy equals 1, is now u equals 1. Equation 2, which was xy equals 2, is now u equals 2, right? Equation 3, which was, so here's equation 3, because remember I remodeled them, which was y over x equals 1, is now v equals 1. And equation 4, which was y over x equals 2, is now v equals 2, right? And then the next thing I would need to do is I would need to find the Jacobian. And the Jacobian is this. Your equation is solved for x, and you take the partial with respect to u. And this, and this, and this. And then Arnie told me something that totally freaking blew me away. He said that instead, if you have your transformations like I have my transformations, instead, and this is really cool, I think, I don't know if you think it's cool, but he said that if you find the determinant of this, u with respect to x, u with respect to y, v with respect to x, v with respect to y, that it equals 1 over the Jacobian. Now I need to know the Jacobian, right? And so if I find something that's equal to 1 over the Jacobian, and so isn't that cool? And so you can have your when you do your substitution, you can do either way. Okay, so when I do that with respect to x, well, that would give me y. And with respect to y, that would give me x. And with respect to x, that's down there in the denominator, maybe I will write that as y x to the negative 1 just for a minute. And so that when I take the derivative with respect to x, the y holds still. And so that's going to be negative y x to the negative 2. I'll fix it. And that was the only that was kind of messy. And then when I take the derivative with respect to y of this, well, I get just 1 over x. And so whatever makes you happy, or x to the negative 1 over x, I'm going to write it as. And I can't help but just want to erase that and write that as negative y over x squared, because I feel like that will be easier when I go to multiply it. So negative y over x squared. Probably should have wrote that on my side piece of paper. And then crisscross applesauce, right? So when I multiply these together, I get y over x. And when I multiply these together, now don't forget it's subtract, and then it's a negative, so it's a plus. And then that is going to be yx over x squared. And then when you reduce that, so this is 1 over j equals, and then this is y over x, and this is plus, and this is the y over x, and so that is 2y over x. Okay, hot diggity dog. And then when I figure out what j is, now before I figure out what j is, don't forget don't forget that when I put things in my integral, that I don't want any x's and any y's. And so, of course, when I put this in my integral, guess what I'm going to have is some x's and y's. And so, but don't worry, we have a way of getting rid of x's and y's with our u's and our v's. And so I can't help but notice right now, and I hope that you're noticing still with me, that when I look at this, y over x equals v. And so this thing right here, which is 1 over j, the Jacobian, is equal to 2v. Now I want to know what j is, so that means that j, the Jacobian, is 1 over 2v. Is that okay? Because I don't want any, when I start to put this stuff in, I want no X's, no Y's. And so that worked out pretty nicely. Okay, so now we're gonna put this crazy thing, we're gonna put this crazy thing together and see how we go, and let's see how we do. Okay, so here our integral is going to be either du dv or dv du. And the good news is you notice that it's going to go on u's from 1 to 2 and from v's 1 to 2. So that's nice. So I can put those on there without even making a decision which one's which yet, since they're the same. Then I don't want to have any y's or any x's. I've got to replace with u's and v's is what I have to do. So that's my next trick, is how will I replace that with only u's and v's? And then I'll have my Jacobian, which I've already got replaced with v's only. And so that's my my next story, is how am I going to make this u's and v's? So I started playing around with that, right? Because because it's a little bit, because of the way I've defined it, it's a little bit different. And I could see where I could become really disappointed sometime and maybe not be able to and maybe not be able to figure it out. So I started off by, because I'm playing around with it, right? The xy squared, I'm just kind of writing that lightly, and I plan, because it's what I had there, xy squared, and I plan on erasing this, is xy times y. And I said, okay, that's good because I know what xy is. Xy is equal to u. And then I had y here. And I was like, oh my gosh, how am I going to handle and get just y? Because that's what I want to have. And so how will I accomplish that? And so what will be my plan so that I can get rid of um all of the y's and turn them all into u's and v's. And so I just started trying a bunch of stuff to see if I could make it work. And so that's what I did. And so I got crazy on trying to figure out what might work, wanting just y. Now I could kind of see that I could maybe go back and try to solve this equation for one of my variables, but I was like determined that, hey, there's got to be a way that I could do it. I started noticing that if I multiplied u and v together, right? So that's x, y, right? This is u and v, y over x, that gave me, this was u and v together. And so I started noticing that if I multiplied them together, that what I got, the x's canceled out and I got y squared is what I got. But I wanted to have y. And so then my idea started to come, well, if you want to have y, why don't you take the square, is this what, did this really cancel out here? And it certainly does. Why don't you take, so I wanted to multiply this together with this, and I get y squared, and I wanted to get y, so why don't I take the square root of that, and the square root of that. And so I started having something like this, and playing around with it, kind of that way. This is actually a different one than, I want to make sure that this works. So if I put this u and then square root of uv, and then this would be, now these numbers for u and v, and so when I'm worried about whether or not when I take the square root, if I would be okay, just real quick, do you notice that they're not negative, right? My variables are always positive. U and V go from positives. So when I go here, this is U, and then this is be the square root, and then U was XY, and then, ooh, U was XY, and gosh, I'm such a dummy. I'm testing this, XY, and then U is XY, and then V is Y over X. And the X's cancel, and that gives me XY, and then it gives me the square root of X squared, which is square root of Y squared, which is Y. So XYY, which is very good. Now, what I did before, I'm going to test it too, make sure that I think they both work, is I had UV and square root of U over V is what I did the last time I did this. So I just figured out a new way that I don't want to lose by erasing it. And um, and just by playing around with it, not getting crazy and solving it using a system of equations or anything like that. So let's see, U is XY, then V is Y over X, and then we have the square root of U, which is XY. Ooh, that's a bigger square root than that. XY, and divided by V. And what is V? V is Y over X. And so out here, I get Y squared. And in here, the X's, when you flip-flop that, because I'm dividing by this, and the y's cancel, and I get the square root of x squared, which is x, and I can do that because everything's positive, and so I can get it out of there. So yeah, either way works. I figured out something different. So I figured out another one that worked, and so I'm feeling vindicated here. So here we get u, and then the square root of uv, and then we have the Jacobian. So times the Jacobian, which is the absolute value of 1 over 2v, and is my Jacobian. That was me making sure that I found something that worked without getting too crazy. And then du dv. And you figure out whichever one you think would be the best to integrate first. Now I put the absolute value in there around the 2v, but v goes from 1 to 2, which is always positive. 1/2 is positive, so I don't need the absolute value. I can move the half out in front, but I can't move the v out in front. And so I have this crazy thing now to integrate 1 to 2, half out in front, and I'm going to have u over v times the square root of uv du. Oh, two integrals, Donna. Two integrals. Okay. U over v, I put the half out, I don't need the absolute value, times the square root of uv du dv. Now, if you're thinking, oh, that's going to be so hard, it's not going to be that bad, because remember that, so you can fix this up and it'll be just fine. And so I'm going to write it here and then I'll just replace it in there. But this is uv, and then this is u to the 1/2, v to the 1/2. And then you can put these u's together. That's u to the 3/2, and v, this is a 1, to the negative 1/2. And then you're going to integrate those one at a time. And in fact, you could, and so that's easy, right? You add one and divide by the same darn thing, and the other one's a constant. And so actually, it's just absolutely fine. And so I kind of did the work here, and then now I'm going to replace that right here. U to the 3/2 and V to the negative 1/2. The answer doesn't turn out that nice, though, even though you might think that it might turn out that nice. And so this is the answer that you get when you do integrate that. So give it a try. Now, I want to tell you that I came up with this transformation myself, and I asked Arnie about this crazy Jacobian thing, and then I went and looked it up. I didn't see it in your textbook, and then I went and looked it up after Arnie told me about it. And it's true. And so that's happy and all of that. And Arnie said that I could sometime have a hard time coming up with the replacement here, and I could definitely see that I could. Professor Leonard, he also did this problem. Professor Leonard, he also got this same answer. And what he used for his was x equals u over v, and y equals v is what he used as his transformation. And so give it a whirl and see that you don't get the same answer. And so the last thing, and then I'm getting myself in my bed. Oh no, I'm not. I'm not a grade algebra quizzes. Darn it. Should I just give them all 15? I don't know if I can do that. I'm so crazy. I don't know if I can. Okay, so I might have to start grading quizzes at 10:30 instead of just giving them all full credit. I don't know. I wanted you, if you wanted to show that if x equals rho sine phi cosine theta, and y equaled rho sine phi sine theta, and z equaled, do you remember where this came from? Rho cosine phi, then the Jacobian would be, and you could go and you could find that. And we already did one that was a 3 by 3, right? So we did a little practice on a 3 by 3. You have to whip out some major trig. Okay, not major trig. You have to whip out some trig, though, to do this. So I'm not going to go major trig, but I thought it was pretty tricky when I did this. And what are we expecting to get? Do you guys remember what the Jacobian was on this? It was rho squared sine phi. And if you're wondering, well, we didn't put absolute value around that. Well, phi, I don't know if you guys remember, but phi had to go between 0 and pi. Rho squared, rho had to be positive, and then when you square it, it's even more positive. Just kidding, it's not more positive, but it had to be positive, and then you square it, so it actually is always a positive value. And if your sign goes between 0 and pi, I'll just remind you how it goes. It's all students take calculus, right? So from 0 to pi, sign is positive. So that's the reason I don't have to have the absolute value around it, and they didn't mention it or anything like that. I actually did it and earlier, and so I'll flip that under there, and so that you can see how I did it. So I even got too tired to write all. I even got too tired to write them all out here, and then I had to kind of almost make lines like a mate in my determinant. I almost had to make lines to separate the little parts, right? Because it was getting so hard. And then you here and then here times here and minus and da 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 and got to it. Okay. I feel happy. I hope you feel happy. And yeah, we do. We all feel happy. Bye.